let's now take another example of a 3-electron pair case. This time we take sulfur dioxide. Sulfur dioxide has this formula. We begin first with calculating the total number of valence electrons in this case. So the valence electrons for sulfur, it is 6 because sulfur is located in group 8A, just like oxygen. So 6 from sulfur, 6 from each of these oxygen atoms. So the total number would be 18 electrons total. The electron pairs would be to divide that number by 2. So there are 9 electron pairs in this case of sulfur dioxide. In order to draw a Lewis structure, okay, we began with that, and then we draw the central atom, which is sulfur. So that's sulfur. This is oxygen, and that's oxygen. And then we draw bonds between sulfur and each of these oxygens. And then we try to satisfy the octet. But we know already that oxygen usually makes 2 bonds because it's located in group 8A. It has 6 valence electrons. It only needs 2 electrons to satisfy the octet. So it will be reasonable to draw a double bond between sulfur and oxygen. So we do that in both oxygen atoms. So now oxygen here has 4 electrons, which satisfy the octet. So that's 6, 8. And here also, this oxygen has satisfied the octet rule by having 8 electrons. So each of these oxygen has now 8 electrons. Now if you add the electrons used so far in this Lewis structure, you would find it's 8 on this oxygen and 8 here. So that's 16. But we had 18 electrons before, so we have 2 electrons to go, or an electron pair to go. If you count the electron pairs also, you'd find it's 2 here, 3, 4, and 4 here, that's 8, but we had 9. So we have 1 electron pair to go, and that would be in the form of a non-bonding pair or a lone pair, which we should write on or indicate on sulfur, the central atom. So therefore, there is a lone pair in this case. Not all electron pairs are bonding. One of them is a lone pair. The arrangement of electron pairs is still trigonal planar. The overall arrangement of electron pairs or the orbital shape is trigonal planar, but the molecular shape will not be, it may not be, and it isn't trigonal planar, as you will see. So let's write that down first. The arrangement of electron pairs or orbital shape, it is still trigonal planar. But the molecular shape, it isn't. Okay, it's not trigonal planar. Why? Because there is a lone pair. So this affects, of course, the molecular structure. We'll see it. So let's write this first. So the molecular structure, okay, will now be different from the orbital shape or the overall arrangement of electron pairs. This is the trigonal planar shape. Now, one of these bonds, well, one of these electron pairs is no longer bonding. It is actually a lone pair. And if you look carefully at this shape, that's a lone pair now, yeah? So this is a bonding pair, that's a bonding pair, and this is an electron or a lone pair. The molecular shape, if you look at this, it's bent or V-shape. So if you can view it as V-shape like that or bent. So the molecular shape in this case is bent or V-shape. The molecular shape in this case is different from the orbital shape because of that lone pair. The angle here will not be 120 degrees. It will actually be less than 120 degrees because of the repulsions between the lone pair and each of these bonding pairs. Okay, these bonds will try to squeeze to try to avoid the repulsions between them and the lone pair, which occupies space. So this angle will not be exactly 120 degrees. It will be less than 120 degrees. So that angle is scientifically represented as less than 120 degrees in order to minimize repulsions between the lone pair, which occupies space, and each of these bonding pairs.